attending my talk. Given the previous talk, maybe I should have gone first, because my size is not going to be sized right now. I'm Razvan. I'll be talking about deploying and managing a massive amount of distributed Elixir nodes. And since probably most of you don't really know who I am, I decided to show you a little comparison, just to start with some humor. Probably most of you know Fred Hubbard. If he's the squid right here doing distributed Erlang on multiple machines, well, this is probably me. I definitely look like I know what I'm doing. I'm lying, I'm not really wearing a red tie. But nonetheless, this is my journey into trying to push the limits of distributed Erlang and also try an alternative overlay network called Partisan. And if you listen to the previous talk and the advice was not to use global, I will totally use global and I'll break it and I'll cause partitions and basically get to about 300 nodes with distributed Erlang and push it to about 900 with Partisan. Let's start with some docs, right? If you look at the Erlang documentation, you'll see that the connected nodes, they have limits there for atoms, the max number of atoms. They have connected nodes, and basically it's just the max number of sockets or ports available in your system. The funny thing is when you connect nodes in Elixir, you never worry about port numbers. It's almost magical. So here I show an example where I start the EPMD daemon, which is responsible for the port mapping that I'm getting at. I started manually with debug mode, and I start the whole distribution supervision tree manually, just to illustrate. And as you can see, there's no node name or host name, and then after we start, we give it a name and a way to resolve DNS. Short names would just use the host name. We'll not try to actually resolve a full DNS. We get a name. This is what you actually see in the Erlang port mapper daemon. You see that node A with the epoch time connected on this port, and node B connected on this other port. And that's again the magic of connecting nodes without even ever worrying about, okay, which port is this node connected? You just connect. Also, another handy tool is calling EPMD with names. That will show you which nodes are connected. And that brings me to the first problem I ran into. After I deployed my cluster, I used good practices and I filtered all my ports. Nothing connected. So it turns out that EPMD and the Earl EPMD assign a random ports, usually like higher number of ports in the system. And that's a problem if you don't control these ports beforehand. So that's one of the first things I had to do and figure out how to actually limit this. And I'll get to how I set up the nodes, but I could have even limited it to just one port. If you're only running one node per machine, then you can really just have one port. And at the bottom there, you see how you can start it if you're just using IEX. So going back to starting this manually, when I run node.start or netkernel start, really what I'm doing is I'm starting this supervision tree with the top there, supervisor called netsup. And this starts the net kernel, which is responsible for managing the network side of things. Earl EPMD, which is managing that separate daemon. So that EPMD is, by the way, that's separate from the runtime. It just, if you run your node with the dash name or s name, it'll also start. But that's a completely separate client. And then we have the auth. And speaking of auth, this is how we manage cookies. And cookies are definitely not for security. They're more for grouping things together, grouping nodes together. When two nodes connect, they negotiate, they do a handshake with the cookie, they MD5 the cookie and they compare that over the network. It's definitely not secure. Otherwise, the traffic is not encrypted at all. So unlike the name suggests, the cookie is not for security. Now I was curious to see if I can create clusters of nodes by changing the cookie at runtime. So I connected a bunch of nodes together, and then I decided, okay, let me see if I can have this node be a super node or something, right? Like that connects two disparaging nodes together. But it doesn't work. The moment you change the cookie, it causes the other nodes, like I'm assuming global causes the other nodes to disconnect, just preventing you from doing that. Again, connections are transitive, so the moment you connect to one node, you'll instantly get connected to the whole network. Global, or also known as the root of all evil, when you try to really scale distributed Erlang, this starts by default, and it maintains the full mesh network. It registers aliases for PIDs, prevents overlapping partitions, subscribes to node up, node down, so you can really keep an update replicated across the network of which nodes are connected together. This is the second problem I ran into. After I reached about 100 nodes, I was connecting and disconnecting, tearing down the whole cluster. Then I noticed that the nodes I would run node list on the server on one of the nodes, and it would just crash completely. And this is what I saw in the logs. Requested disconnect to prevent an overlapping partition. So what happens is global, if it detects that a node is down, it will broadcast a message across the mesh with that node identifier and basically cause all the other nodes to also disconnect from that node, just to prevent partition. And I suspect because of the chatter, because I'm starting this completely default, I'm not changing anything on purpose, I'm not optimizing, I was causing those net ticker times and heartbeats to not reach the nodes, and all things went pretty bad. So this was the other flag. I mean, I did what's sensitive, just disable it, right? And again, if you're running this in production, maybe you shouldn't. Maybe you shouldn't use global, but definitely do your own research to figure out what this will change with your setup. Now, down to the real limits and why, at least in my naive, unoptimized setup, I was running into bottlenecks. When you start Distributed Erlang and you send a connection request to another node, there's something called a port driver that is usually not Erlang code, and that's actually the interface that provides I/O syscalls to the Erlang runtime, and that the way that works depends entirely on the operating system. So, for example, if you're on FreeBSD, you have kernel polling with KQ, versus if you're on Linux, you have epoll. So that, based on the research I've done, it matters a lot in terms of how much throughput you can support. But ultimately, at the end of the day, everything has to go through one TCP connection. This driver and the net kernel, like eventually through a socket acceptor pattern, will open a socket, but it'll send everything through that. Heartbeats, messages, and probably through something called head-of-line blocking, you'll eventually get to a point where you won't be able to even send heartbeats, let alone the internode communication. And speaking of traffic, actually, this is very crude, but because I filtered the Erlang port mapper ports to a range that I knew, I could easily just TCP dump for a period of time, and kind of I was just curious to see what kind of chat, how many pockets am I seeing here, and even from going from 200 nodes to 300 nodes, that's quite a jump. That's 1.2 gigs per minute across the whole network. So that's pretty significant. I guess if you're running in AWS and you're not paying for internode bandwidth, that's okay, but that is definitely a significant amount. Now, this is my setup. I could have chosen many ways to connect those nodes. Probably Kubernetes would be what most of you would connect with. There's multiple strategies out there in the default libcluster library that most people use. In my case, I went for pure separation and just went with EC2 instances. I started with T2 Nano. I did have to upgrade this a little bit because it turns out that the I/O chatter between the nodes kind of killed my little T2 Nano instance. But the setup was pretty simple. I used Terraform to provision the instances, and Ansible to install Erlang, upload the distribution. I just tar-zipped it, upload it, run it. And as I'm experimenting with the cluster, it just helped to tear it up and down. The strategy to connect the nodes is something linked into libcluster. It's called EC2 tags. It uses the metadata API that I think every instance in AWS has access to. So from that, you can get the node's private IP, and that's what I used to connect the node. So as these instances are put up, they just connect. It's very, very simple. And EC2 tags has a poll interval. I think the default is 5 seconds or something like that. So every 5 seconds, it will poll this, connect the nodes together. Again, because it's transitive, doesn't really matter what that list is, because I think the EC2 library uses a map set to actually give you the nodes that are not connected. But again, there's multiple ways to connect them. I highly recommend you read the libcluster library. It's super small, and it will give you some understanding of the various ways you can connect, including the DNS cluster that Chris McCord talked about in the keynote. That's a super simple library and very easy to understand. So I have this cluster up and running, and it's idle at this point. So I'm trying to measure things as I try to break it. I crossed out the measured, and I added plan to measure, because in between deploying this cluster, I realized that what I was trying to measure, well, actually, to backtrack, I was trying to figure out when you would do this, right? Because if you're WhatsApp, that makes sense. You'd connect all these nodes. It's a massive chat application. But if in a regular situation where you're running regular server workloads, it's very hard to find a use case. The most I could think of is maybe real-time bidding or something like that, or I don't know, maybe I didn't have enough time, but maybe play around with WebRTC and try to see if you can actually handle video streaming like that with multiple nodes connected. But these type of metrics that I initially thought of wouldn't really be conducive of measuring any of that stuff. So later on, I kind of switched to using PubSub and just figured out that it's more appropriate as the cluster size increased. But nonetheless, I'll go through this. The results are pretty uninteresting. I think for 300 nodes, the latency is negligible. But nonetheless, I created this benchmark module. I got inspired from this project called DE Bench, Distributed Erlang Bench, and it runs on every server. Once the benchmark starts, it will go through all the nodes that are visible for that current node and execute all these remote spawns and calls. Also, the node that I'm initiating the benchmark from does a spawn on all the nodes. So the benchmark kind of starts on all the nodes together, and the chatter starts. I'm measuring this with telemetry spans, and I have a RabbitMQ cluster that those messages get pushed to, and I just ran this locally. I have a consumer, a Broadway consumer that records this. This is kind of what I saw. It's pretty non-interesting. I decided to look at another interesting thing. I didn't have any visibility into how many nodes are actually staying connected, right? Because I shoot this benchmark and I don't really know what's going on. So I added for each metric received, each node also checked the whole network. So it ran node.list.length. And I also recorded this. So what you see here is, for example, for a 100-node cluster, all the nodes are connected. These are the messages, right? Because I'm flooding the network with messages. What's interesting is for 200 nodes, I can already see that some of the messages, as they arrived, the nodes were already not connected to the network. And that's at the 200 number. For 300, that's even crazier. So what this told me was that the network was still unreliable. Somehow, this was the breaking point, basically. So the next thing, I actually did this while I was here. I decided to try it one more time. And this is where I both upped the instance size, and I played with the net tick time. Because I suspected that all the chatter going around between services will not allow the heartbeat to reach the nodes in time. And it turns out I was correct. I don't really have any meaning behind those numbers. You can see the defaults there. So the tick intensity is 4 seconds, and tick time is 60 seconds. So when I bump those to 100 seconds and 200 seconds, respectively, all the nodes were connected all the time. Now, I guess there's a trade-off. I don't think that means that I solved the problem. It just means that I am less able to detect failure, but I also decrease the chatter, so that's not bad. I guess the bottom line is that when I ran the tests again, all the nodes received messages. So that told me that even though my heartbeat, like I kind of prevented error detection, no errors really happen. Like no failures. No failures happen, which is great. Now on to the pub sub. So the pub sub test was pretty simple. Each node starts a pub sub server and subscribes to the same topic, as you can see here. So what I do is I broadcast a message to the whole network, and I record how many nodes receive it and the delay. Again, the delay is negligible. It's almost instant. So I didn't even include that. What happened was, as you can see here, so basically up to 300 nodes, I would see the broadcasted message on every single node. So 100% deliverability. When I reached 300 nodes, I saw like 2% loss. And what that meant was the node was not connected to the other node. So of course, it's not going to receive the pub sub broadcast. the protocol itself. Doesn't care. It will just shoot the message. If you're not there connected to receive it, then you'll not receive it. This I fixed with that setting that I showed previously. So now there's less chatter, nodes are connected, the network is more stable, and everything's good. I think I could have pushed this probably to at least 500 nodes with distributed Erlang if I cheated the net tick. But this is where I stopped because I thought, okay, you know what? I saw the breaking point of this. Let's try the other fun library that I wanted to try, which is the point of comparing the two. So Partisan. So this was a PhD thesis by Christopher's, and what's impressive is that he released not only an Erlang library, but also modifications to things like React Core and a suite of tests and everything around it, so that you can essentially easily write a network overlay that provides an alternative way to connect the nodes. The topologies it supports, the full mesh that is basically the equivalent of distributed Erlang. There's a client and server. And the one that I was interested in, the peer-to-peer, that was basically the one that's the most able to support, I guess, like super large clusters. They claim about 10,000, I think, but that's probably just a theoretical size. So the way the nodes are connected, we don't have a full mesh anymore. We use something called hybrid partial view, and the way this works is as you connect the network, it builds this directed graph where you have two views for each node. There's an active view and a passive view, and the passive view is there as a backup. So if one of the active nodes disconnects, a node from the passive view is promoted as an active view, and you can tweak the parameters, how many nodes you want in the active view, how many nodes you want in the passive view. And this coupled with another feature of Partisan, where instead of having just one TCP connection that handles the membership and heartbeats and everything, you can set up special channels. And even within the channel, you can set up a setting called parallelism, which will configure the number of TCP sockets that are open. So for example, if you have a super large cluster, you can set up a separate channel just for that and tweak it that way. Now, of course, now the problem is our nodes are not all connected anymore. So the way I was running my pub sub test is not going to work anymore. In order to connect like a sparsely distributed network, now you need something like a gossip broadcast to do it. And the most naive way to do it would be if you want to send a message from node A to node L. There you see it; they're not directly connected. Node A will basically look at its active view, send a message to all of those nodes. All of those nodes in turn, if it's the first time they see the message, will do the same thing. It will flood their active view. And as a best effort, hopefully the message will get to the intended node. I heard there is a way to enforce deliverability for this, but that's not something I was planning to explore. But that's definitely a difference there, and it's a compromise, I think. Now connecting the Partisan nodes, there's not much out there in terms of orchestration. Luckily, libcluster is pretty flexible. So if you configure a custom strategy that I had to write, you can also pass in MFAs for connecting, disconnecting, and listing nodes. And what you can see there is I pass in like the connect MFA is a Partisan peer service, which handles the connection for the nodes. These are the channels that I mentioned earlier. So for PubSub, for the PubSub test, I used a separate PubSub channel and have separate connections in there. So messages go through uncluttered by all the chatter of the network. Another difference, right? Remember this. So this is a library. This is not an alternative distributed Erlang. This I think the point of the library was that the point of it being a library was that it should be easily testable. So if you're running a system right now and you don't want to switch perhaps OTP versions and so on, you can just run this as an application layer, disable distributed Erlang completely, and just connect it this way. And this is an example of a node spec. So that's how you join two nodes together. There's a set of channels and a listen address there. You also don't use, you don't need Erlang port map or daemon anymore if you're using this. I also had to write a simple PubSub adapter. The docs are amazing there. So I just based it off the existing PG one, I believe. It's very simple. You start the top of the line there is how you configure it. So this starts on every node again, just like last time. I give it a name and the adapter. So that adapter would start my special server that has a few things. One of them is when you do a Plumtree broadcast, Partisan requires you to implement a handler, a broadcast handler. And this handler is invoked, is again present on every node, and it is invoked when you receive a message. So a funny thing happened as I'm testing this. I looked at the behavior and I implemented all the methods. One of them is merge. So when a node receives a message, it's supposed to figure out if it saw the message before. And I just returned true everywhere, just to test it out. And that caused my broadcast to keep repeating forever. Like I just generated millions of messages until I figured out I should use something like an Etsy table to, very simple. Like I'm just storing the UID in there. I'm checking if it's there. If it's there already, then I mark it as stale and it won't propagate. But it's quite interesting to see this working. And again, I ran the same test here. I got to about 900 nodes. Pretty good deliverability, I think. 886 nodes received the broadcasted message. And I thought that was an interesting use case. If you think about how Phoenix can support, I don't know, 2 million WebSocket connections, if you multiply that by at least 500, let's say, or you get good deliverability, you can potentially see how you can connect a massive amount of people in one chat room. Maybe close to 1 billion or something like that. That was it. Thank you very much. I'm listing my GitHub repos here.